Hey, this is section 4.1. We're talking about related rates. Up until now, we've been looking at derivatives, which are in the context of being a function of x and y. So usually we write y equals, there's x's in the equation, like for example, y equals 3x squared plus 2x plus 7. And we've talked about how derivatives are rates of change. It's how is this x value changing as this y value changes. And in math, a lot of times we are in terms of x and y. But in physics and a lot of the sciences, we're looking at the position of an object versus the time. And so a derivative then becomes not a rate of change between x and y, but of position and time. And that's what we're going to do in these related rates problems. You've got kind of a format for how you're going to approach these. I'll write a little list. We might add to it a little bit later. The first thing is you're going to identify, I don't know why that D is capital, but identify what is being measured and pick an equation. So the equation that you're going to use depends on the context of the problem. For example, this first example that we're going to do is talking about a spherical balloon being filled with air. And so what we're talking about is the volume of a sphere. So that would be your equation. If we're talking about a triangle, maybe it's a trig equation or a Pythagorean theorem. If it's a box, maybe we're talking about surface area. Okay. Then the second thing is to substitute for any extra variables. Okay, sometimes there's too many variables and you have to substitute in and decrease the number of variables we have, and I'll show you an example of that. And then you're going to take the derivative with respect to time. And then you're going to plug in values. Alright, we'll make some sense of that list as we go through the examples. Alright, so first we've got a spherical balloon. So I'm going to draw a picture here. I'm taking a drawing class with my son. So I'll do a little shading. That'll be exciting. A little shadow. Light's coming from the left. It's very exciting. Okay, and here's the circumference around here. So we're going to call this distance right here, this is the radius. Okay, we've got a volume. So I look at this and I say, well, what am I measuring? This guy's being filled with air, so filled implies volume. I'll tell you something else. The labels on these things really are helpful. If you have a label with a cube in it, that's talking about volume. If you have a label with a squared, it's talking about area. And if you have just no power, it's length. So let's write those down because I think that helps. We're talking about length if it's like a distance per time, so like meters per second or feet per second. We're talking about an area if the label is distance squared per time, like feet squared per time or meters squared per time. And then it's a volume if it's a distance cubed per time. And a lot of times that'll be a clue as to what you're looking for. So I see this cube right here and I'm like, all right, we're doing a volume, and the shape's a sphere. So the volume of a sphere is 4/3 pi r cubed. Now, a lot of times I kind of skip step 2, substitute for extra variables, until I get to the point where I realize I have them. Because sometimes it's just as easy as taking the derivative and going. Okay, so let's look at our variables. Anytime you have a rate, that is a derivative. because derivatives are rates. So I look through this problem and I say the balloon's being filled at 2 centimeters per second. That is a rate on a volume. So this is going to be dV. So I wanted to do that in red. This is going to be dV. Oh my gosh. Sorry. dV dt. The change in the volume with respect to time. That's going to be 2. Okay. Now, the question is, how fast, again, that's a rate, so we're talking about a derivative, is the radius increasing? So that's going to be dr dt. So basically what we're doing in this section is instead of saying dy dx, we're saying d whatever over dt, because everything's with relation to time. So if the volume is changing, it's dV dt. If the radius is changing, then it's dr dt. And this is what the question is asking for, is how fast is the radius increasing? That's the question. And then I've got one more piece of info in this problem. It says the radius is 3. R equals 3. Okay? So that's the information that I know. Now, go back up to your list. The order that these are written in is very important. Take the derivative with respect to time first, then plug in values. Okay, so don't plug in 3 into this derivative before you do step number 3. Okay, let's take the derivative. The derivative of v is dv dt. And the derivative of this, although it looks complicated, is just a simple power rule, because 4/3 and pi are a number. So this 3 is just going to come down in front. So this becomes 12/3 pi r, and the power decreases by 1 squared. And then you can reduce if you want. dv dt equals 4 pi r squared. And when we take the derivative of our r value, because everything's in relation to time, we also put dr dt at the end. So it's almost like everything gets a label. Every letter that you take the derivative of gets a label. Okay? And that actually happens in polynomials too. Let me just pause with this for a second. When you have y equals 3x squared plus 2, and you take the derivative of y with respect to x, and then you do the derivative of this is 6x, derivative of x with relation to x. But because this is in relation to itself, dx over dx is just 1. So we just write dy dx equals 6x. Okay, so it's it's actually been happening all along that we're labeling each of these derivatives like we are down here. It's just that dx over dx has always been 1. Okay, now once you've taken the derivative, now we're just going to plug in. So r is going to become 3, dr dt is what we're looking for, and dv dt is going to be 2. So I get 2 equals 4 pi r, 3 squared dr dt, and then you just solve for the thing that you're looking for. Okay, so because I only have one unknown left at this point, I know that step 2, sorry, trying to scroll, it's not scrolling. I know that step 2 didn't need to happen. We substitute for any extra variables. We don't have extra variables. We only have one unknown, so we're good to go. Okay, so I divide by all this stuff, and I think it ends up being 6 pi equals 2, and dr dt equals 1 over 18 pi. I don't care if you go decimals or fractions here. You can go either way. And the label on this, because radius is a length, okay, we go up here to our labeling techniques. Our lengths are measured in distance per time. So we're looking at, our problem has centimeters and seconds. So this is going to be 1 over 18 pi centimeters per second. So that means that the radius changes with relation to time 1 over 18 pi centimeters per second. All right, let's try another one. There's power in the repetition. Start to see patterns. Okay. A car A here is traveling west, and it's traveling at 50 miles per hour. Okay, we'll come back for that. We're going to call this like this length A here, just to correlate from car A traveling that path. And then car B is traveling north. Okay, at 60 miles per hour. We'll call this the B's road B. And both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 from the intersection? So anytime a problem talks about the measurement between two things, that's a straight line, a right angle or a straight line, depending on the picture. So if I want to know at what rate they're approaching each other, what I'm looking at is their distance to each other. Okay, and I'm going to label that distance C. All right, now let's go through this problem and figure out what we've got here. First of all, this right here I know from the label is a rate. It's 50 miles per hour. And that is the rate at which A is traveling. So that's a derivative. So it's going to be dA dt. Okay, and that's going to be 50. Now, car B is traveling. This, again, is a rate, but it's a rate of car B. So that's going to be dB dt. Okay, both are headed for the intersection of two roads. At what rate are the cars approaching? So the question is also a rate. Rate, are they approaching each other? So another way of saying that is, what's the rate of that distance between them? So what the question is asking for is what's dC dt. Okay. Good, and then we keep reading. When car A is 0.3 miles, now look at the label on that. That is a straight up distance. That is not a rate. Okay, so that just says that A is 0.3 miles. Okay, and then the last piece of info here is car B is 0.4 miles from the intersection. So again, that's just a straight up distance. It's not a rate. Car B is 0.4 miles. All right, that's all our info. Now, we need, all of these things right here are talking about A, B, and C. So then I look at my picture and I go, what formula do I know that relates A, B, and C? We think hard for a minute and we go, hey, wait a minute, I remember pre-calculus, Pythagorean theorem. Okay? And then we take the derivative. So, derivative of 2a is 2a, and then we've got to label it, dA dt. Chain rule, it's the chain rule. Okay? And then we've got 2b, dB dt, and then 2c, dC dt. Okay, plug some stuff in. I've got dA dt is 50, A is 0.3, got a 2 out here. The B value is 0.4, and dB dt is 60. 2, I don't know what C is, okay, and dC dt is what I'm looking for, right? Okay, so you go, wait a minute, I don't know what C is. I've got too many unknowns here. No, you don't, because look, if you know what A and B are, you can also find out what C is, right? So a squared plus b squared equals c squared. That relates these guys. So we have 0.3 squared is 0.25. Just kidding. I added them all together at once. 0.3 squared plus 0.4 squared is 0.25. All right, there we go. And then we're going to square root that, and we get 0.5 equals c. Okay, so that tells us what this value is right here. And then we could do some quick math. Let's see, I think this ends up being 78 here on the left side. And then we get 2 times 0.5 is 1 dc dt. All right, so dc dt is going to be 78. Now, label. We're talking in miles per hour. It's a distance rate, so it's miles per hour. And that's our answer. Okay, so pause this video and go try example 4.2 from the book. That'll be a good one to kind of, it's similar. Okay, you can try that. All right, welcome back. Hopefully you actually did that. Next problem. A man walks along a straight path. All right, so we'll put him here. Extra points if you draw fun pictures along the way. Makes it exciting. And a searchlight is located on the ground 20 feet from the path. Okay, so let's put the searchlight here. Okay, and it is 20 feet from the path. So I can label this actually 20 because it's not changing. So everything else up until now, the distances, like let's go back up here. This says that they want to know what's the rate, at what rate are the cars approaching when car A is 0.3. Car A is not always 0.3 miles. Car A is moving along this line. And so that's why you can't plug that value in for A right away, because it's constantly changing. I'm looking for a rate at a specific moment, and so that's why you plug these values in after you take the derivative. Okay? Whereas in this situation, the light is actually not moving. It's static 20 feet from the pathway, and so you can actually label that 20 from the get-go. And the searchlight is, it keeps focused on the man. So it's like this, but it's also moving. You know, as he goes further this way, it'll go like this, and it'll go like this. So you ask yourself, what's changing? Well, the length on this is changing, but also this angle. So let's see what they're interested in. At what rate, see, because it could be this angle or it could be the length there. We're not sure. At what rate is the searchlight rotating, okay, when the man is 15 feet from the point on the path closest to the searchlight? So we're looking at the rotation, not the length of the beam. So what we're interested in this picture is theta. So we're going to erase that and label that theta. And then he's walking, and this distance we'll just call A. That's changing. And we're not interested in this hypotenuse right here. There's nothing in the problem that talks about that. And that's what's going to dictate what formula we use. So I look at this and I'm like, it's no longer Pythagorean theorem because we're not talking about the three sides. We're talking about this angle and two sides. Well, that sounds like a trig function. So this is your opposite side and this is your adjacent side. And if you remember from trig, that's a tangent function. So tangent theta is opposite over adjacent. Okay, that's our equation. And let's talk about what we've got. He walks on a straight path at a speed of 4 feet per second. That's a rate. and that's a rate of this distance. So this is dA dt is 4 feet per second. Searchlight's located on ground 20 feet. We talked about that. At what rate is the searchlight rotating? So they're asking about the angle d theta dt. That's what we want to know. When the man is 15 feet from the point on the path. This is a distance. So here's the point on the path that's closest to the searchlight, and when he is exactly 15 feet away, that's the distance of A. All right, let's take the derivative. The derivative of tangent is secant squared. And don't forget that it's a chain rule, so derivative of the outside function is secant squared, evaluated at the inside function times the derivative of the inside function. Okay, so you've got to have that label on it. And then this right here, don't do the quotient rule on that. That's just 1/20th A. You can rewrite that this way. That's what that means. So it's just a simple power rule. This is 1/20. A to the 0, if you will, and then dA dt. That's your derivative. Now we're going to plug in values, okay? D theta dt, that's what we're looking for. dA dt is 4. Now, I don't know what theta is. Oops, hold on. And if I don't know what theta is, then I've got too many variables. So again, this is a situation where that step 2 comes in. You're going to have to make a substitution. So theta, well, I look up at the picture. Is there any way to figure out what theta is? Well, if A is 15, then I have this equation that relates theta to my exact position. So tangent theta is 15/20, and if you go inverse tangent of both sides, you get 0.6435. Now I'm operating in radians, okay? If you want to do it in degrees, that's fine. Just label the degrees. So that means that I'm going to plug in right here 0.6435. Okay, and then crank this out. I'm going to divide by secant squared 0.6435 on both sides. And when you calculate that number, I think you get 0.128 radians per second. I'm going radians because I'm in radians, and then it's a rate, so it's per second. Okay, you can now go do example 4.3. I think that's, yeah, 4.2, 4.3. And it's a very similar deal. You're going to set up a trig function and practice with that. All right, last one. I think this is our last one. I want you to have lots of examples. Water is draining from the bottom of a cone-shaped funnel. All right, so here's my funnel. And I've got water in it here at some level. And that water is changing. That water height is changing because it's coming out, okay? So let's label some stuff. The height of the funnel is 2 feet. Okay, so the entire funnel here is 2 feet. And then the radius is 1 foot. And then we want to know about the water and the height of the water. Now that's changing, so we can't put a concrete number in for it. We have to label it a letter. So I'm going to call this, the radius of the water, R, and this right here, H. So the rule is this: if something in your picture is changing, it has to be a letter until you take the derivative. But if something is static, then you can label it a number. So this cone's not changing. Okay, so that's why I can label it 2 and 1. But the water is, so they have to be R and H. Okay, let's figure out what information we have. Water is draining from the bottom of the cone at rate of 0.03 feet. Look at the label, cubed per second. That is a volume rate. So dV dt. That is 0.03. Okay. The height of the funnel is 2. We've got that labeled. The radius is 1. At what rate is the height of the water changing? So the question is about a rate of the height change. So dH dt is my question. When the height of the water is 1/2 foot. So that's just a straight up distance measurement. So it's not a rate. So H is 1/2 foot, but again, that water is changing, so you can't plug 1/2 in right away. Now, I'm going to walk myself into a little bit of a hole so you can see what this looks like. So don't be frustrated. It's helpful to see how mistakes develop. Okay, I might take this because, we've been doing a lot of these problems now. I'm getting the hang of them. And I'm going to say, okay, I'm going to take the derivative. So the derivative of V is dV dt, okay? And what I have here is actually a product rule. I've got two variables. Okay, I'm going to take the numbers with the R. It doesn't matter if you do that or put them with the H. Either way, they're a product. So I'm going to say the derivative ddt now of the first term times the second term plus the derivative of the second term times the first term. All right, so the derivative of this first term is going to be 2/3 pi r dr dt times my height. And the derivative of this h is just 1 dH dt. Okay, now look at what happens. I go, okay, dV dt, I've got 0.03. I've 2/3 pi. The radius, I don't know. dr dt, I don't know. The height is 1/2. dH dt is what I want to know. And 1/3 pi, and again, r, I don't know. So I've got 1, 2, 3, if you count the r twice, you got 4 places where you have unknowns, which is way too many. Like up here, we had some unknowns, like we didn't know what theta was in this problem, but I had a direct relationship with theta from my picture, and I don't have that here, okay, and on inspection. So in this situation, I realize I've got too many variables and I need to get rid of one of them. So I need to figure out, all right, I want to get rid of R or H in this problem, one of the two, okay, because there's too many. And looking up here, because I've got a bunch of information about H, I'm thinking I probably need to get rid of the R. That's the problem here. So I look at this picture, and this is maybe a little stretch. It's probably been a little while since you've had geometry, but welcome to calculus. We use everything here. This picture in this cone has two similar triangles, and this is a really common picture that you see in geometry. Let me draw this a little differently here into the middle. Okay, so this is the radius of the cone, which we said was 1. This is the height of the cone, which we said was 2. And then in here is a tinier triangle that is the radius of the water and the height of the water. And if you remember from geometry, if you have two triangles embedded in each other, if they're right triangles, they are similar, which means their sides are proportional. So I can actually set up a little relationship between all these sides. The short side of the big triangle to the short side of the small triangle equals the long side of the big triangle to the long side of the small triangle. Okay, and if you solve this, you get h equals 2r. So I have a choice now. I can take 2r and plug it in for h and get rid of h, but like I said before, I've got actually a lot of information about h. I probably want to keep that around. So what I'm going to do instead is I'm going to solve this for r. So r equals h over 2, and this is going to go in for my r. Okay, so I actually, this doesn't work. Okay, I'm going to start over, which is all right. It's fine to try something and fail. And I'm going to plug in h over 2 instead of r. Okay, but it's squared. The formula says squared, so make sure that stays on there. And let's simplify this a little bit before we do the derivative. This is h squared over 4 times h, which is, I'm going to hit this 4 and the 3 together. So this is pi over 12, and then you've got h cubed. All right, now what's cool about this is not only did we get rid of the r, but we also got rid of the product rule. So now the derivative is a little bit easier. 3 pi over 12 h squared dh dt. Don't forget that label, if you will. So this is going to be pi over 4 all right, now we can plug in our info. dv dt, let's go up here. dv dt is 0.03 pi over 4. The height, what do we figure? That's a half. And dh dt is what we're looking for. Do a little bit of algebra. Oops. I just found a mistake, which I will fix and explain. But it was up here a little ways, so I do not want to redo this whole part of the video, so just bear with me. The answer is negative. The reason is because, let's change this. I'm going to put it in blue. Here's what I want you to see. Water is draining. That means that this volume right here of the water is getting smaller. It's going down. So this is actually a negative 0.03. Okay, so anytime something is decreasing in volume, you give it a negative sign. Okay, and that means that when you plug this in, this is a negative, and that makes this a negative. Now, it's a funny thing, these signs, because it could be that you don't put those signs and then you just say, there's two ways to do this. You either assign a negative sign because it's draining, and then your answer ends up being a negative because the height is decreasing. Or you cannot deal with the signs, but then in words you can say, the height is decreasing at a rate of 0.153. And that implies to the person that, yeah, that is a negative value and it's going down. Your book does negative, and because it's a multiple choice, like on your homework, you're going to probably need to put the negative sign. But if you want to do that in words on your test, I'm okay with that. All right, so the height is decreasing, and what's our labels? Feet per second at 0.153 feet per second. And that's your answer. Okay. Now, I think that's it. I want to go check something up here. I had this thought as we were going through these problems. I want to clarify this and just make sure you're clear. When we were up here doing this sphere balloon, I wrote down these right here. And I think I said this, but I want to make sure that I'm really clear. These labels are all rates. So these are all your derivative labels. It's not straight up length. It's a rate of change of length is distance over time. A rate of change of area is distance over time, and a rate of volume is a distance cubed over time. So it's not a length on its own is going to be just a distance, like centimeters, okay? But the rates are going to be per time. All right. I think that's all. So try some of these. This is a big practice makes perfect section. The more you do, the easier these become. And listen, I promise you, I'm not a word problem person. I'm not real great at those, but these do get easy if you practice them. So give it a go, and we'll